Hello, everyone. In this lesson, I wish to cover intermediate value theorem. This is a very important theorem in calculus. Okay, intermediate value theorem. Okay, so I'm going to, I just type the name of the theorem. Okay, for short, this theorem is called IVP. Okay, so I put an H there. So intermediate value theorem. So we're gonna see why it is called intermediate value theorem and its interpretation, and then its application. So excuse me, I'm a little bit, my voice is a little bit affected by the weather, but I think it's audible. Okay. Anyway, the interpretation, well, the content of the theorem is very well explained, of course, in the textbook with very, very well illustrated pictures. So I'm going to use this piece to get started. Okay, suppose f is a continuous function on the closed interval. Let's see if you guys can see it. Yes, you can see it. Okay. So f is a continuous function, okay? So now we're going to dissect this theorem to identify which part, which part is the theorem, what is the premises, right? What is the premise and what is the conclusion? Okay, what is the premise or what is the conclusion? For each theorem we study, we must be able to tell, so what condition we need to check before we can apply the theorem, right? So the content of the theorem is that suppose f is continuous on a closed interval, okay? The word close is, even though it's not necessary, but it is important. The way it's written, the interval is written is a closed interval. Okay, so to write the word close is to emphasize the condition is so important. Now, first one, f is a continuous on a closed interval. Secondly, n be any number between f of a and f of b, where f of a is not the same as f of b. Then you may think, oh, what if f of a and f of b are the same? Well, that case will be considered a trivial case. And so to deal with non-trivial case, so here we assume f of a and f of b are not the same. Then there exists a number c in the interval ab such that f of c is equals to capital M. Okay. So when we read this, there are two major assumptions, okay? Two major assumptions. The first one, of course, f is continuous, and secondly is continuous on a closed interval. And the second one is f of a and f of b are not the same. It didn't say which one is larger, which one is smaller, but they're just not the same. Okay, so the interpretation I would like to start with, to help you to understand this theorem is to, first we understand what is a function. Okay, what is a function? We know that a function is a rule that assigns an input exactly one output. Okay, so that's what we put a function. And we know that, comes with function, there's a definition, there's a domain and range, right? So in the rule for a function, right, the rule is f, for example. This f will assign each input exactly one output. Okay, so input is one category of data, output is another category of data. So for input, okay, let me boldface, okay, input X is being assigned, okay, after the function is applied, the rule applied to it, it produces an output. Okay, so when you look at the theorem, right, you look at the theorem, f is a continuous function, right? F is a continuous function on a closed interval, but you know, first we have to put the numbers in their proper category. Okay, so for example, what is f of a? What is f of b? F of a is when the input a, okay, the function f applied to it produces f of a. F of b, same thing. So a is in the category of input, f of a is in the category of output, and f of b is in the category of output. Now, what is n? N be any number between f of a and f of b, right? So capital N is in the category of output. So there's a capital N there. There's a capital N there. So N is in the category of output. And what is C? C is in the category of input. Okay, so input C, okay, after the function is applied to it, right, it produces an output, and that output is going to be capital N, and capital N is between f of a and f of b. So first we need to understand that. If C is an input, certainly we have f of C. F of C is a capital N. So first we understand the categories of all of these different quantities. They're called different names. So X is in the category of input, A is in the category of input, A, B, C, you can see they're lowercase, and the output is f of X output, f of A output, f of B output, f of C output, and a capital N is in the category of output. So now what the theorem says is that, so let's dissect the condition. Okay, so let me put it right here. Okay, let's put it right here. The first condition is f is continuous on closed interval AB. The word close is necessary and it is not necessary. Necessary to emphasize the importance of a closed interval. It's not necessary because, well, this interval is given as a closed. Okay, on closed. So this is not entirely necessary. So to make it simple, I'm going to make it simple. Okay, so number two is that capital N is between f of A and f of B. F of A and f of B. F of B. Okay, and provided that f of A and f of B are not the same. So they're not the same. Okay, so we're going to put a not equal sign in between these two. All right. So I'm going to try to make it shorter. Okay, but these are the two conditions. Okay, if are these two premises, okay, if these two premises are satisfied, Okay, if these two premises are satisfied, the conclusion is what? Okay, if the condition is satisfied, what conclusion can we expect? The conclusion says there exists, okay, then there exists a number C. And where is C? C is in the category of input, and C is also in the interval. Okay, this means in. Okay, there exists a number C inside the interval. Okay, you see this open interval now. The requirement is closed f of a, and the C is inside. This also means that C is greater than A, okay, and less than B. Okay, such that f of C is the same as capital N. And capital N is chosen arbitrarily between f of A and f of B. You can see in the textbook, there's some very good illustrations. I'm going to just use these textbooks. You can find these textbooks, the same author textbook or any calculus textbook. They all have very good illustrations. The first one, you can see figure 8, right? So you can see the categories. A, C, B, they're in the category of input. So input is horizontal, on the horizontal, right? The output is on the category of output, f of A, capital N, capital B, right? So you think of the definitional function, so we understand that. Between f of A and f of B, we can choose any number arbitrarily. And you draw a horizontal line, and there will be an input C between A and B, such that f of C is equals to capital N exactly. So in this case, we have exactly one C. In this second case, look at the second case, right? In the second case, if N is chosen to be a different number, right, between f of A and f of B, and there are multiple C's. In fact, in this case, 1, 2, 3. And in the theorem, it said there exists a number C. It doesn't tell us how many. So sometimes there's one, sometimes there could be more. Is it possible we have 10? Totally possible, totally possible. But we always have at least one. This theorem, when you use this word, there exists a number, basically is telling us that there is such number, there are at least one of them. And in the case there's only one, you can see there's one. So the theorem doesn't tell us how many for any specific circumstances. So we have to deal with them case by case basis. Okay. So figure 9 expresses similar situation. Okay. F of A and F of B. The difference F of A and F of B in figure 9 is F of B is smaller than F of A. And in this case, in AB, F of A is less than F of B. So it doesn't matter which one is bigger, which one is larger. And this is always true. Okay, always true. Now, how do we apply this theorem? Right, so now we understand what is what, right? Input, output, it's all about input, output. For each input between, well, for each input, we have exactly one output. That's what function is. The fact is f is continuous on every number on this closed interval. We also understand that meaning, all right? The definition of continuous function applies. So when you take limit, you just do direct substitution, if necessary. But oftentimes, this theorem is used in a very special circumstance. Okay, so I'm going to call it a corollary of the theorem. Okay, I sent it to your pronto, okay, yesterday. A corollary to IV intermediate value theorem. What is that? The corollary of intermediate value theorem is more commonly used, okay? In terms of the premises, I'm going to copy and paste. Okay, I'm going to copy and paste. Okay, and show you what has changed. So corollary to this intermediate value theorem, even though it was not listed in the textbook, but it was used. It was used. The first condition stayed the same. Okay, the second condition is the following: is that f of A and f of B, the product of these two numbers is negative. If the product of these two numbers is negative, right, it satisfies this condition, because if two numbers multiply, one is a positive, the other one has to be negative to make it negative, right? So these two numbers are opposite in sign. So of course, f of A and f of B are not the same. Now, if f of A and f of B are not they're surely not the same, and they're opposite in sign, and between these two numbers that are opposite in sign, there's a number 0. Okay, the conclusion, well, the theorem you already guaranteed, there's, for any n, you can pick a number, there's a c such that f of c equals to n, and now we pick n equals to 0. This intermediate value theorem guarantees that there will be an input c from this interval such that f of c is equal to 0. Okay, this theorem is very, very useful because it helps us to find the roots of functions, find the solutions to equations. Okay, that's why this latter theorem, the corollary, is more commonly used. Okay, so let's look at some examples. The first example, I would say, look at the textbook. The textbook has a very nice example. So, what it does is actually uses the corollary. Okay, so I'm just going to explain it here. You can read about it. So we have a function. And we want to solve this equation. So we're going to find the root of this equation. And it's obvious that factoring and whatever we do is going to be difficult. Okay, so if we use intermediate value theorem, then we are going to see which interval can possibly give us the solution. Okay, so using the corollary, and we first set up a function. And this function, because it's a polynomial is, continuous everywhere on the number line, right? And certainly it is continuous for the closed interval between 1 and 2. So the first condition is satisfied. And then on this step, it checks f of 1 and f of 2, which is f of A and f of B. You see, one is negative, one is positive. The second condition is satisfied. So we know there is a c. The c is going to be the root, and such number exists. We are assured that there is a solution between 1 and 2. So this theorem and the corollary often help us to determine the existence of solutions. And how do we find the solution is quite another matter. You have to, try it. in this case, and it tries different numbers and even make the interval even smaller. Okay, so they keep shrinking the interval until they can have a decent approximation. But for most of us in this section, we just want to apply the theorem. We want to demonstrate a solution exists. A solution exists. Okay. So let's look at some homework questions using intermediate value theorem. Using intermediate value theorem. And I also put some of these on your homework. Okay, so let's take a look. Let's take a look. These are on your homework. Okay, so I'm going to move this over. And I'm going to move this piece over here. I'm going to bring our how we use it, right? All of these are homework questions. So there's a first category of such questions is that the interval is given. The interval is given. If the interval is given, great, right? We just apply the theorem, right? And that's it. Okay, and I apply some of the theorems to guarantee continuity. But there's another category that the interval is not given. If the interval is not given, then we have to find it. Okay, how do we find it? Try it now. But since we know we're going to use the theorem, right? So we just try to find those A, B such that the conditions are satisfied. Okay, so let's look at the first one, number 53. Okay, so the first example. Okay, so, well, the instruction is pretty clear. It says use the intermediate value theorem to show that there is a root of the given equation in the specified interval. Okay, the interval is given. Interval is given. I'm going to bring the corollary under so we can use it, right? So it's available to us all the time. Now, so in the first one, it asks us to solve this, to show there is a root. It didn't tell this to show there is a root. There's a root. So the equation goes like this: x to the power 4 plus x minus 3 equals to 0. Okay, and the given interval is open 1, 2, between 1 and 2. Okay, now, so the function, right? So we're going to choose the function. So what function would that be? Of course, the function would be this piece, right? Function. This is a function, and this is a polynomial. This is a polynomial, right? So the first condition that f is certainly continuous on 1, 2, but we do want to mention it. However obvious it is, right? In showing work mathematically, sometimes we have to point out the most obvious fact just to make a point. Okay, when students are assessed, we just want to know this condition need to be checked. All right, so here we can say f of x is continuous on 1, 2. This has to be closed interval. Why it is continuous on 1, 2? Because f is a continuous, right? It's a polynomial. F, right? A polynomial. It's a polynomial. A polynomial is guaranteed to continue to be continuous. That's our theorem number 5 and theorem number 7, right? So it is certainly continuous on this closed interval. And secondly, the product is negative. So we're going to have to evaluate f of 1, right? And we also have to evaluate f of 2. Okay, how do we evaluate f of 1? Right here. So replace x by 1. 1 plus 1 minus 3, obviously that's going to be negative. You don't have to give the exact value, right? And we're going to evaluate f of 2. So when x equals to 2, and that's going to be positive, right? So second condition is also satisfied. So we point that out. F of 1 multiply f of 2 is negative. And then once these two conditions are checked, and we can quote the definition, right? We can quote the conclusion directly. Okay, then there exists, and then you may say, according to, right, according to intermediate value theorem, there exists a number c between 1 and 2 such that f of c is 0. What does that mean? That is, what is f of c? F of c would be this piece replaced by c, that's equals to 0. So there exists a solution. There is a root. There's a root. And that's all we need to do for this one. You're finished. You're finished. Okay. So let's look at another one. Let's look at another one. Okay. This time we're going to do, we did number 54 in class, and let's do number 55. That's our second example. Okay. So this time we have e to the power x equals to 3 minus 2x. And the given interval is 0, 1. 0, 1. Okay, so that interval between 0 and 1. So this equation, to apply to apply intermediate value theorem, we need to know that we have to create a function. So how do we create such a function? What if we don't create a new function? The nature, so I'm going to have a little discussion here. What is the meaning of this equation? Right? This equation actually is pretty tricky to solve using algebraic technique. The nature of this question is basically, if you see a function on the left as a function, and you see 3 minus 2x as another function, when we set them equal, that's what the equation is an if statement, right? So when they're the same, okay? So I'm going to draw a picture to explain you the nature of this question. E to the power x, right? If I draw a picture right here, okay? I'm making some adjustments from -2 to 5, from -2 to say 10, right? So that's the curve e to the power x. And how about the other curve? 3 minus 2x, 3 minus 2x, okay? 3 minus 2x, I'm going to use a different color. Okay, say purple. Right, so this equation is about to find the point of intersection between these two curves. Excuse me. Okay, so solving this equation is to find the intersection. Okay, find the intersection between these two curves. It looks like there is a solution. There is a solution. Okay, but that solution, it looks like it's not really 0.5. It's between 0.5 and 1, right? Since here we only want to confirm the existence of a solution between 0 and 1, it didn't ask us to find the actual solution, so we can think of using intermediate value theorem, of course. Okay, so we're going to create a function. So if we create a function, right, we're going to create a function so that both curves are involved. And how do we create such a function? The technique to create such a function is to make 0 in the given equation. It makes 0. So I can have, I'm going to add a 2x on both sides, subtract 3. So I'm going to add a 2x, adding 2x on both sides. Okay, so 2x, negative 2x, and move to the other side. And I'm going to minus 3 on both sides, minus 3 on both sides. So this way you have created a new function is created. A new function is created and it is equal to 0. Okay, and this will give us the clue as what function should be introduced. We're not going to use this one, we're not going to use this one, and we're going to use something, you know, we do the algebraic manipulation so that we can apply the intermediate value theorem, and this is the function we're going to use. Okay, let's see what it means. Okay, so I'm gonna introduce this function, and we're gonna do a graph. Okay, typically you don't need to do this, but I just want you to understand this transformation has some real meaning, you know, graphically. Okay, so if I draw this picture, okay, if I draw this picture there, it certainly is a new function. Okay, it's a new function. I'm going to adjust the view from -2 to 5, and here -2 to 10. It's about the same scale, right? And this one goes down further. Maybe I can go a little further. There we go. Okay. So if you compare these two pictures, okay, I'm going to set the pictures side by side so you can see better. Okay, so make this, I'm going to make this screen a bit larger. Okay, I'm going to set the picture to side by side. Okay. Cancel. So compare these two pictures side by side. With similar scales, 10, 5, -5, I'm going to make this -5. There we go. Solution that was here, right? That was here. The solution we're looking for is really the point of intersection. The point of intersection. So the solution we're looking for is here, right? And in about the same place, it's the same solution. It's the same solution. The input is the same solution, but in this case, it is it's x-intercept. So by doing this transformation, creating this function, the question to find point of intersection between two curves becomes to find the x-intercept of this one function. I hope you understand that. I hope you understand that. Okay, so this is the graphical interpretation of it. So creating this function, right? We did some algebra, adding 2x, subtract 3, but it does have some real impact. We have transformed the question from finding the intersection between two curves into finding the x-intercept of one curve. Now, then we just apply the corollary, okay? If you like to, pause and do your own work and then come back to do it, that'll be fine with me. That'll be fine with me. Okay, so I'm just go ahead to apply to this function, we created this function, and then obviously this function is continuous on AB, right? So we're gonna bring this question. I want to show you how I quote it. F is continuous on AB, which is 0, 1, right? Why it is continuous? Because e to the power x is continuous on its domain, which is guaranteed by which theorem? Theorem number 7, right? Theorem number 7. And the linear and 2x minus 3 is also 2x minus 3 is a polynomial, is also continuous. It's also continuous on, we can just say it at the same time then, right? It's a polynomial, and they are continuous on, the entire number line. And of course, it is continuous on this closed interval, right? We quoted that theorem, so we know why. And number 2, we have to demonstrate f of 0, f of 1, they're negative, right? The product is negative. So to demonstrate that, we're going to have to do some calculation. Okay, so this is equal, and we're going to bring our function. This is our function, right? When x is replaced by 0, and that equals to, it looks like this equals to 1, and that's 0, that's going to be negative. F of 1, right? You can use calculator if you want. 2 times 1, but in most cases, you don't really need calculator. E is 2.7. 2.7 plus 2, that's more than 3, so it's just going to be positive, right? Then you can say i.e. f of 0 times f of 1 is negative. Positive number times negative number is negative. That condition is satisfied. And then we can apply the conclusion. And what is our conclusion? There exists a number. There exists a number C inside the interval 0, 1, such that f of C equals 0. You can see the more you quote this theorem, the better off you are. Okay, you don't need to create much of sentences at all. You just quote the theorem, and with that means that is what, right? We are looking for solutions for this equation after all, right? So f of C. C is here, so that number C will make 0. So that's certainly the root, and thus, right? If you want to demonstrate further, you can you can move that equal to 0, you can move the 3 and 2c to the other side. So you can write it as 3 minus 2c to the other side. And that is exactly what we're looking for, right? We're looking for solution to this one. So this is a matching to that. So we have a solution. It's basically just say, hey, we have a solution. The theorem guarantees the solution. The theorem guarantees the solution. Okay, and that is done. That is done. All right. That was 55. 56. Let's try 56. 56. Okay, that makes our example number 2, and now example number 3. You may like to pause this and try your own. So we have sine x equals to x squared minus x, right? The same argument, but if you look at from the two curves, if you see two curves, one is sine, one is x squared. So this discussion, right, of the nature of the question, right, is to find intersection. Oh, pardon me, I left out the interval. 1, 2, 1, 2. And of course, we know sine curve, right? So this is to find the intersection between two curves. There we go. Intersection between two curves, right? And now what is x squared minus x? X squared minus x. We're going to plot that curve, right? We have a different color, purple. There. Oh, look at that. We have to make some adjustment to that picture, right? So let's do it. Let's do it. The view, we're going to go from -2 to +5. We can make adjustment. Okay, -2 to 10. There we go. And you can see these two curves actually has 2 points of intersection. But between 1 and 2, there's just one intersection, right? Had we have a different interval or larger interval, it might have two intersections. So from -1 to 2, we have 2 points of intersection. So the two solutions we're looking for, the two solutions where we want to be certain, whether we have such a solution between 1 and 2 is really this input, okay, the C, right? So the C in this case is, so if we create a new function, right, we talk about creating new function. By creating this new function, our new function will look like the following, right? You move everything to one side. You have sine x minus x squared plus x. This is our new function. But this new function, right? If I graphed it, this is x-intercept. This is x-intercept. Okay. Let me clean this up a little bit, right? If we set the curve side by side, you see similar things. Okay, between 1 and 2, I'm going to make a little adjustment to this picture here, right? So you can see there's the same scale. I want you to see them in comparable scales. So here, right? So on this one, I'm going to make adjustment to the view, which is going to be from -2 to +5. And from -2 to +5. Let's see if that works. There we go. There we go. Between 1 to 2. Between 1 to 2. Right? Between 1 to 2. So this is the point where this is the number we're looking for. And this number turned into is still between 1 to 2, is at the same place. Is the x-intercept. It's the x-intercept. So then the transformation doesn't change the answer. Doesn't change the answer. It's just it's a way of handling the problem, the question, to demonstrate the existence of such a solution. And of course, it's pretty hard to estimate from the graph, but we know it's between 1 and 2. And in this case, we just want to prove the existence of such point. Okay. Without further ado, so let's get to the solution. Okay, let's get to the solution. Hold on. Okay, this part of when you show work, you don't have to show the reader, but I do wish you to understand this. The nature of the question, and how we handle it, right? So now let's look at the solution. Okay, so we certainly created this function where you usually say let, right? Let the function be such. And then you just check the conditions, right? Sign is continuous everywhere. So we can say f is a continuous on 1, 2 close interval. You must mention this interval as a close interval because the theorem calls for it, even though it is, continuous on both open and closed. You must mention that interval as the theorem required. Okay, it's continuous on 1, 2, right? Theorem number 7, if you want to quote that, by theorem number 7. Right, theorem number 7 illustrated, well, it says all the polynomial, all the trig functions, all the rational functions, all the exponential logarithm functions, inverse trig function, they're all continuous in their domain. Number 2, you're gonna do f of 1 and f of 2, right? So f of A, f of B, so you just check the condition, have it well organized. F of 2, right? So you're gonna separate, you can calculate separately and plug in the function, right? F of sine of 1, and this is 1, and this is 1. What is the value? If you don't have a calculator, you can see this makes 0, but what is sine of 1? Well, you can use a calculator, that's good to know, but this 1 certainly is treated as a radian. Okay, 1 is treated as a radian. If 1 is treated as a radian, what is sine of 1 if you are to estimate it? Well, 1 is less than pi over 2, isn't it? Right, pi over 2 is 3.14 divided by 2, that's about 1.57. So this is definitively positive. Okay, this is definitively positive because of what? The radian 0, 1 is larger than 0, and is less than pi over 2. Okay, I don't have a calculator, even I can use the software, but I just want to demonstrate and review some trigonometry for you. Okay, This median 1 is in the first quadrant. Okay, so it's going to be positive. Sign is positive in first quadrant. Now, 2. What will this be? Well, sine of 2, whatever its value it is, it's going to be less than or equals to 1. Okay, sine of 2. You don't have to know its actual value. Okay, -1 less than +1. Okay, sine of 2 is between these two numbers. So this is less than 1 or equal to 1. The max is 1, but this is definitely less than 1. Suppose this is the max, so 1 plus 2 is 3. It's still less than -4, right? So this is going to be negative, right? Even if you don't have a calculator, you can still estimate, and estimate, that's all we need. Okay, that's all we need. That's really all we need. We just need to know the sign, right? We don't need to know the actual value. As long as we know the sign, right? So in this case, we have just verified that, right? You can say E f of 1 times f of 2, the two numbers of opposite sign, the product is negative. Then you just quote the conclusion. Quote the conclusion directly. Then, right, you may like to say, by intermediate value theorem, there exists a number C such that f of C is 0, but A, B need to be replaced by 1s, 2, and that's it. That is, right, you do want to elaborate a little bit, right? F of C, right, f of C is going to be right there, and that's going to be 0. So there's a solution. Right, so sine of C equals to C squared minus C. We have demonstrated there's a solution. There's a solution. Okay, so that's the end of this question. This is the end of this question. I think that's all for this lesson. I will talk about intermediate value theorem for another case where the interval is not given, then we have to find it ourselves in another lesson. Thank you for watching.